In section 5.2, we will study solving systems of differential equations using the method of elimination. But first, we're going to review direct substitution. We're going to jump right into some examples. You're going to pick this up easily based on what you know about solving algebraic linear systems by substitution. In example 1, we're looking for the general solution. Notice we have a second order system. We have two dependent variables, x and y, and let's assume that our independent variable is t. So the solution to this system is a pair of functions, x of t, y of t, that will balance both of those equations simultaneously. So the idea of solving this system is similar to the idea of solving an algebraic system by substitution or elimination. I'm going to isolate one of the variables in terms of the other variable. Looking at equation 1, we could easily solve for y in terms of x. Then we could use that information and plug it into the second equation, thus eliminating a variable. So looking at equation number 1 and isolating y, can we do that in one step? Y would be equal to 1/2 x double prime minus 3x. Again, I just rearranged equation number 1 and isolated y. We want to plug this into equation number 2. Notice equation number 2 has a y right here, but it has a y double prime over here. So in order to substitute, we're going to need to go ahead and find a couple of derivatives. So y prime is going to be 1/2 x triple prime minus 3x prime, and y double prime then is 1/2 x fourth derivative of x minus 3x double prime. So we're going to take this and we're going to plug it into equation number 2. Equation number 2 is y double prime equals 3x plus 7y. I'm going to substitute what we found from equation number 1 into equation number 2. Notice on the left here we have y double prime, and that's what we found right here. So substituting gives us 1/2 times the fourth derivative of x minus 3x double prime over there on the left side. On the right side of the equation we have equals 3x plus 7 times y. Up here we have y in terms of x. So we'll have 7 times 1/2 x double prime minus 3x. Notice we have arrived at a single differential equation in terms of x alone. So the goal of this substitution method is to rewrite the system in terms of a single variable. By the way, you could have certainly solved this for isolated x first and then plugged that into the other equation. It doesn't matter which variable you find first. So let's simplify what we have here. I'm just going to do a little algebra over there on the right side. Let's call that 7/2 x double prime minus 21x. Then let's move everything over to the left side. Let's see, we have negative 3x double prime. On the left, we need to subtract 7/2, so negative 6/2 minus 7/2 would give us negative 13/2 x double prime. On the right side, we have 3x minus 21x, that's negative 18x, and we'll pull that over here to the left side, 18x. Let's go ahead and multiply through by 2 to simplify. We would get the fourth derivative of x minus 13x double prime plus 36x equals 0. This is a fourth order linear homogeneous differential equation with constant coefficients. Remember, that means we can solve it with the characteristic equation. In this case, our characteristic equation would be r to the fourth minus 13r squared plus 36 equals 0. Make sure you don't put a 36r there. If we factor this, we get r squared minus 4 times r squared minus 9. So the roots of our characteristic equation are plus and minus 2 and plus and minus 3. So again, you may need to review chapter 2. Once we know that we have distinct real solutions, we can go ahead and write our solution in terms of x. We can write the function for x. So the solution for x of t is c sub 1 e to the negative 2t plus c sub 2 e to the 2t, distinct real solutions. Remember, this is the pattern for expressing your general solution. C sub 3 e to the negative 3t plus c sub 4 e to the 3t. So we have half of our solution to the original system. Keep in mind, you can write those terms in any order. When you're checking your answers in the back of the book, just make sure that you have the substance, that you have the correct terms, specifically looking at the exponents on the e, but your coefficients, again, can be in any order. Just like with an algebraic system, we're going to use back substitution to figure out the function y of t. So hunting back through our work, we need to find an equation that relates y and x. And if we look right here, we have y in terms of x. But if we want to write y in terms of x, we're going to need x double prime. So let's go ahead and take a couple of derivatives here. So x prime is negative 2 c1 e to the negative 2t plus 2 c2 e to the 2t minus 3 c sub 3 e to the negative 3t plus 3 c sub 4 e to the 3t. Let's go one more derivative. We obtain 4 c sub 1 e to the negative 2t plus 4 c sub 2 e to the 2t plus 9 c sub 3 e to the negative 3t plus 9 c sub 4 e to the 3t. So again, using this as our guide, let me just make a note of it over here. Y is equal to 1/2 x double prime minus 3x. So we're going to multiply, let me just write this in here. We're going to multiply x double prime by 1/2, and we're going to subtract 3 times x. Okay, so I'm going to write this down directly, making those calculations in my head as I go. So 1/2 times the term from x double prime minus 3 times the term from x prime. So 1/2 times the term from x double prime, that's going to give me 2 c1 e to the negative 2t minus 3 times this term right here. So 2c1 minus 3c1 gives me negative c1 e to the negative 2t. Let's do that again for the next term, and I'm just combining like terms. 1/2 times 4c2 e to the 2t, that would give me 2c2 minus c2 e to the 2t. Again, that was 2 minus 1. Let me make sure I did that right. 1/2 times 4c2 is 2c2 minus 3c2. Yes, that gives me minus c2 e to the 2t. Okay, moving on to the next term. Combining these like terms, 1/2 times 9c3, that gives me 9/2. 9/2 minus 3c3. I better write that one down. 9/2 minus 3. That's going to give me 3/2. So we get plus 3/2 c3 e to the negative 3t. Looks like same thing's going to happen here. 1/2 times 9c4 minus 3c4 is going to give me 3/2 c sub 4 e to the positive 3t. It's a pretty straightforward process, but as you're seeing, there's a whole lot of details. So just messing one little sign up can cause you to work these problems several times until you get it right. So take your time and be careful. These two functions, x of t and y of t, together represent the solution to the original system. But I do want to bring your attention to, if you're checking your work in the back of the book and your constants or the order don't necessarily look exactly like what you obtained, what you want to do is look for pattern. For example, if you look up your answer in the back of the book And this term says negative C1 e to the negative 2t, and this one said positive C1 e to the negative 2t, then it would still have the same relationship between those two terms. Remember that those constants are arbitrary. They represent values which we could obtain from initial conditions. So I'm just looking at overall pattern here. So what I'm checking is to make sure that these two have the same coefficient but opposite in sign. So you might want to be aware of that as you check your work. So that is the method of substitution. We're going to go ahead and work another example. Notice this is a lower order system. This is just a first order system. So we did a more difficult one first. However, do notice that this is a non-homogeneous system. So I wanted to throw this in here so you would know how to handle it when you had a non-homogeneous system. We will begin with the same approach. We're going to choose one equation and isolate one of the variables. Looks like it will be convenient to use equation number 1 and isolate y in terms of x and t. So from equation number 1, we obtain y equals x prime minus 4x minus 2t. That minus 2t is what causes it to be a non-homogeneous system. We're going to need to substitute this information into equation number 2. In equation number 2, I've got a y over here, but I also have a y prime over here. So I'm going to need to find the first derivative before we start substituting. So differentiating each term with respect to t, we get y prime equals x double prime minus 4x prime minus 2. Remember, we are differentiating with respect to t. Now, we're going to plug this information into equation number 2. Equation number 2 is y prime equals negative 2x plus y. So we're going to take the information that we obtained right here, and we're going to plug that in for y prime. We get x double prime minus 4x prime minus 2. Our goal here is to write everything in terms of x alone, so we're eliminating y, equals negative 2x plus y, and y lives up here, plus x prime minus 4x minus 2t. Next, we're going to rearrange this so we have all of the terms containing x on the left and our non-homogeneous terms on the right. So we end up with x double prime minus 5x prime. Let's see, over here on the right side we have a negative 6x, so we're going to pull that to the left to get positive 6x. And moving our constant and our term containing t over here to the right, we have x double prime minus 5x prime plus 6x equals 2 minus 2t. At this point, it's just like the previous example. However, now we can see that we have a second order linear non-homogeneous differential equation. So we're going to need to solve a non-homogeneous DE. Let me remind you that the solution to a non-homogeneous differential equation is the sum of the characteristic solution plus the particular solution. This part comes from the corresponding, the characteristic equation for the corresponding homogeneous equation. This term, remember, comes from the assumption of the nature of the non-homogeneous term matching the right side of the equation. So again, this is what we learned in Chapter 2. If you need to go back and review that, that is good. So let's determine the characteristic equation for our differential equation. We would obtain r squared minus 5r plus 6 equals 0. And we could factor that r minus 2, r minus 3 equals 0. So the roots of our characteristic equation are real and distinct, which means we can represent the characteristic part of our solution as c sub 1 e to the 2t plus c sub 2 e to the 3t. That's part of the solution. Now we need to find the particular term. Now remember, one method you could use for finding the particular term is to make an assumption about the nature of this particular term matching the nature of the function on the right side. The other option was variation of parameters. Remember that formula with all the integrals? This part involves a little bit of guesswork. The variation of the parameters is a direct solution. You can use either way, either method that you prefer. So I'm going to assume that x sub p of t has the same nature as our non-homogeneous term. I've got a linear function on the right, so I'm going to write this as a general linear function. Then we're going to plug this into our differential equation. So we're going to need a first and second derivative. And then we're going to sub it into this equation right here. X double prime is 0. We're going to have minus 5x prime, that's minus 5b, plus 6 times x, x is a plus bt. That is equal to the right side 2 minus 2t. So let's group our constant terms together and our linear term together. Then we set corresponding coefficients equal. So I want my constants equal and I want the coefficients of t to be equal. We obtain the equations negative 5b plus 6a equals 2 and 6b equals negative 2. Well, from that second equation, we can see that b is negative 1/3, and then we can use that information over here to solve for a. So we end up with a equals 1/18. So b is negative 1/3 and a is 1/18. Let's put our solution for x all together. So remembering that our solution x of t is the characteristic part plus the particular part, we end up with the characteristic part was c sub 1 e to the 2t plus c sub 2 e to the 3t. And then we tack our particular term. The form of our particular term is right here. We know a is 1/18 and b is negative 1/3. So that is half of the solution to the original system. Again, the only difference between this and the previous example, other than the order of the system, is dealing with that non-homogeneous term. At this point, we want to go and back substitute and figure out why. I'm going to go back to this first equation, and I can see there the relationship between x and y. To determine y from x, that equation indicates we're going to need a first derivative. So I'm going to go ahead and find a first derivative. We get 2c1 e to the 2t plus 3c2 e to the 3t. The constant goes away, and we have negative 1/3 there on the end. Okay? Now, using this as our guide, let me just write it over here. We can see y is equal to x prime minus 4x minus 2t. So we're going to take x prime, this equation, minus 4 times x, and then we're going to add a minus 2t on the end. So negative 4 is what I'm multiplying by here. Let's generate our solution y of t. So we're going to take the term from x prime, 2c1 e to the 2t, minus 4 times the corresponding term from x of t. So we would end up with 2c1 minus 4c1. That gives me minus 2c1 e to the 2t. And we're going to just tack that minus 2t onto the end. Okay, next we're going to go to this term, x prime, 3c2 minus 4x minus 4c2. That's going to give me minus c2 e to the 3t. Okay, continuing, we have x prime, negative 1/3 minus 4 times 1/18. That gives me negative 5/9. And then there on the end, we have x prime. Remember, we're subtracting 4 times x. So this is going to be plus 4/3 t. Probably should have put my constant term there on the end, but that's okay. So that is the solution to our linear system. I need to backtrack just a minute. Did y'all notice the mistake I made here? We are working on the last term. We're looking at x prime minus 4 times x. In x prime, we have this negative 2t term. So negative 2t minus 4 times negative 1/3. That's negative 2t plus 4/3, or negative 6/3 plus 4/3. That should give me negative 2/3 t there on the end. Okay, caught it in the nick of time. So there is our two functions that balance the original system. So in both of these examples, we were solving using a substitution method. In the first example, we had a higher order system, but it was homogeneous. In example 2, we had a lower order system that was non-homogeneous. So you may want to review how to solve a linear, non-homogeneous differential equation with constant coefficients. We're going to press on now to another option for solving linear systems, part 2, using linear operators. You have probably seen the big D as a differential operator, but maybe not in this particular context. Definition: a linear differential operator of order n with constant coefficients is of the form capital L equal to a sub n d to the nth power plus a sub n minus 1 d to the n minus first plus, continuing for any number of terms, plus a sub 1 d plus a naught, where d represents differentiation with respect to time. So we're dealing with a linear operator. If you'll remember, both differentiation and integration are examples of linear operators, as well as the Laplace transform. The Laplace transform was an example of a linear operator. This in particular is our linear differential operator. Again, you've seen the big D for the differential operator, but we're going to look at how we can write a differential equation using that notation. So, for example, write the following equations using linear differential operators. So right here, the double prime indicates I've taken a second derivative with respect to t, or whatever our independent variable happens to be. So instead of x double prime, I'm going to say a second derivative of x, and I indicate that as d squared. Second, we have x prime. That's a first derivative. So we're going to do minus 3 times the first derivative of x. No derivative on this term. And then all of those terms have an x in common, so I'm actually going to factor it out. And we have 2d squared minus 3d plus 1 x equals 0. It's a whole new way of writing a differential equation that you probably haven't seen before. We can do this with systems as well. Now, before I write this using linear differential operators, I'm going to write both of those equations in standard form. That is, I want all my x's together on the left, plus my y terms, leaving either the non-homogeneous term, in which case we don't have for this equation, or 0 on the other side. For the second equation, I'm going to order it negative 2x plus y prime minus 3y equals 0. So I want all my x's on the left column approximately, y's in the right column, and then over on the other side of equals, either the non-homogeneous term or 0. Rewriting equation number 1, we could call that d minus 1 times x plus 2y equals 0. And equation number 2, negative 2x plus d minus 3 times y equals 0. So notice I went ahead and factored out the x. This would be d times x minus x, but we factored out the x to obtain this. So it's a pretty straightforward, easy way to express differential equations or systems. Now, if I write it like this, then I can actually treat that big D, which represents derivative with respect to time, algebraically, and that's what we're going to do next. In general, any 2 by 2 linear system can be written in the form L sub 1x plus L sub 2y equals f sub 1 of t. L sub 1 and L sub 2 are linear differential operators. So in our previous example, L sub 1 would be d minus 1. L sub 2 would be 2. L sub 3 here would be negative 2, and L sub 4 would be this d minus 3 term. Okay, so that's what the L's represent, whatever operators we have there. Using a form of Cramer's rule, we can find the solution to the system as follows. On the left side here, we have the determinant of what's called the coefficient matrix. We're going to label that the operational determinant. So these are the linear differential operators that we obtained from rewriting that system with our new notation, times x equals, now look what we have over here. On this side, notice we have taken the constants of the system and replaced column 1 of our coefficient matrix with those functions. So again, you can see Cramer's rule being applied here. The only difference between this and Cramer's rule is that normally we see Cramer's rule expressed as a quotient. So if we were to isolate x and divide both sides by this determinant, it would look more like Cramer's rule. Remember, we write it d sub x over d. So this part is like the d sub x from Cramer's rule, and this is like the d from Cramer's rule. Similarly, over here in the second equation, whoops, please correct a typo. That x is supposed to be a y. So we have our coefficient matrix there on the left side, same as what it was for x. And then on the right side, notice we have taken the constants of the system and replaced y's column. If we were to solve for y, this would look like d sub y over d from Cramer's rule. So we just have it written a little bit differently. Note that the determinant on the left-hand side of the equations is known as the operational determinant. If the system is homogeneous, then the right-hand side of the equations vanish identically. That's math humor. You remember what that means? That was from chapter 1. That's a real fancy way of saying they are all equal to 0. So if these functions over here are all 0, then we have a homogeneous system. If they are functions of t alone, it is a non-homogeneous system. In either case, you can solve it using this form of Cramer's rule and operational determinants. So in example 4, we're going to use this new method, use operational determinants, and Cramer's rule to find the general solution of the system below. Now, if your system is homogeneous, by the way, and both of these functions are 0, then this determinant on the right-hand side is 0. Both of these would end up being 0, and it's a pretty easy thing to solve. So for our example, I have chosen a non-homogeneous system. So when you get to your homework and those harder problems, you'll know how to solve this, applying it to a non-homogeneous system. The first thing that we want to do is rewrite our system using linear differential operators. So I'm going to begin by just rearranging the equation. I'm going to scoot way over here so I can have plenty of room. X prime minus 2x minus y equals 0. And the second equation becomes negative x plus y prime minus 2y equals negative e to the 2t. We want to rewrite that using linear differential operators. So equation number 1 can be expressed, first derivative d minus 2 times x minus y equals 0. And the second equation, negative x plus d minus 2y equals negative e to the 2t. So we're going to begin forming this first equation. We're going to take our operational determinant, the determinant of our coefficient matrix, multiply it by x, and set it equal to this determinant here. So setting up this first equation, following this as our guide, we end up with the determinant of d minus 2, negative 1, and d minus 2 times x equals, now for this determinant, I'm going to replace x's column by the functions on the right side, 0 and negative e to the 2t, and then I'm going to keep y's column the same. Treating the left-hand side, those big D's, as if they are algebraic expressions, And following the pattern of a 2 by 2 determinant, we're going to find our forward diagonal product, and then we're going to subtract our reverse diagonal product. I'll just keep it in red. So we have d minus 2 times d minus 2 minus our reverse diagonal product, negative 1 times negative 1. All of this applied to x is equal to, on the right side, forward diagonal product is 0. And our reverse diagonal product, we're going to have negative e to the 2t times negative 1. Working on the algebra on the left side here, we have d squared minus 4d plus 2, and then this gives me a minus 1. So this becomes plus 1x equals negative e to the 2t. Okay, that should be plus 4 minus 1. How about a plus 3? Factoring on the left side, we have d minus 3 times d minus 1. Well, let's do it this way. What does this mean? This means x double prime minus 4x prime plus 3x equals negative e to the 2t. You're going to see that the roots of the operational determinant are the same as the roots of the characteristic equation. So if you don't want to convert back to variables, you want to leave it in operational determinant form, you can do that as well. But just to make sure we understand the process, I'm going to go back to what is familiar. Now, the characteristic equation for this differential equation is r squared minus 4r plus 3 equals 0. So again, this factorization would be the same as if I factored my operational determinant, and I get r equals 3 and r equals 1. So the characteristic function is c sub 1 e to the 3t plus c sub 2 e to the t. However, we have a non-homogeneous term. So let's assume that the particular function has the same nature. We'll call it a e to the 2t. We'll find a couple of derivatives. And then we'll plug it into this equation right here. X double prime is 4a e to the 2t minus 4 times x prime. 4 times x prime is going to give me 8a e to the 2t plus 3 times x, 3a e to the 2t equals negative e to the 2t. Okay, so combining our constants here, notice all of the terms have an e to the 2t. So we could say 4a minus 8a, which is negative 4a, plus 3a, negative a equals negative 1. Therefore, a equals 1. So the particular part then is e to the 2t. Therefore, we've got our solution for x. We can say, therefore, x of t equals the characteristic part, c sub 1 e to the 3t, plus c sub 2 e to the t, plus the particular part, right here, we found out a is equal to 1, so plus e to the 2t. There's half of our... Okay, we are halfway there. We have x of t, now we need to find y of t. Now if we come back up here to our plan, we are going to follow this formula, now this time for the variable y. The operational determinant on the left is going to be the same as it was before, but the determinant on the right is going to be a little bit different. So let's write that down following that guide to see what we end up with. We're going to have the same operational determinant that we had previously. This time applied to y equal to, now on the right side, I'm going to keep x's column the same, but I'm going to replace y's column with the functions on the other side of the system. Now, if I calculate the operational determinant on the left, it's going to be exactly the same as it was for x. On the right side, though, it'll be a little bit different. So forward diagonal product is d minus 2 times negative e to the 2t. We're going to subtract our reverse diagonal product, which turns out to be 0. So doing a little bit of algebra over here on the right side, we get d times negative e to the 2t plus 2e to the 2t. So I'm just distributing here. We have to understand that that represents the first derivative of negative e to the 2t. Calculating that derivative, we get negative 2e to the 2t plus 2e to the 2t. So this means that the equation we need to solve for y is homogeneous. Observe, if I rewrote this in terms of y and determined the characteristic equation, it would be exactly the same as the characteristic equation that we had before. We would also obtain the same roots and the same form of our characteristic function. There would be no need for a particular term since this is a homogeneous differential equation. We can say, therefore, y of t is, now I'm going to use different constants here. Above with x we have c1 and c2. I'm going to use c3e to the 3t plus c4e to the t. Now that's pretty good. We have x and y. It feels like we've solved the system. But notice I've got 2 arbitrary constants for x and 2 arbitrary constants for y. That did not happen when we solved by substitution above. We only ended up with, looking at our first order system here, we only ended up with 2 arbitrary constants. So we want to make sure and reduce the number of arbitrary constants, and we're going to do this by substitution. So using the operational determinants, you've got a little bit of extra work at the end to reduce the total number of constants that you use. So here's how we're going to do it. I'm going to pick either one of these equations. I'm going to pick this one because it looks a little easier. And I'm going to plug in what I have for x and what I have for y, and I'm going to find the relationship between those constants. So in equation number 1 up here, we need x prime. So I'm going to differentiate x as I go. X prime is 3c1 e to the 3t plus c2e to the t plus 2e to the 2t. We're going to set this equal to 2x plus y. And we've got y right here. So we're going to do 2 times x. I'm thinking multiply this one by 2 and add it to this one right here. And we'll combine like terms as we go. So 2c1 e to the 3t plus c3 e to the 3t. We end up with 2c1 plus c3 e to the 3t. Okay, moving on to our second term, 2c2 plus c4 e to the t. See if I can write it where it's readable. We had 2c2 plus c4 e to the t, and our last term, 2 times x plus y, we end up with a plus 2e to the 2t out here on the end. Okay? Notice if I subtract that 2e to the 2t from both sides, that's going to cancel. And then I want to set the coefficients for e to the 3t equal and the coefficients for e to the t equal. So I'm going to take coefficient of e to the 3t on the left side, which is 3c1, and I'm going to set it equal to the coefficient of e to the 3t on the right side. So notice we can obtain the relationship between c1 and c3. Subtracting 2c sub 1 from both sides, we get this relationship c1 equals c3. Now, setting coefficients of e to the t equal, we get c2 equals 2c2 plus c4. So the relationship here is negative c2 equals c4, or you could say c2 equals negative c4. Either way. So I'm going to use these relationships to go back and refine my solution for y, and then we're almost there. So finishing out the second half of our solution, y of t equals C3. Well, C3 is the same thing as C1, so we can now call that C1 e to the 3t. Then we have plus C4. Well, C4 is the same thing as negative C2 minus C2 e to the t. So little extra work there at the end, but we have successfully solved the system. All right, that was a lot of detail. Now might be a good time to pause the video, go grab a drink, and come back ready, refreshed to do applications. Part 3, we're considering our theme for the semester, mechanical vibrations. We've looked at this in many different ways. Today we're going to be looking at a coupled spring mass system, modeling that with a system of differential equations and solving with our new methods. So we're going to be applying this method of operational determinants and Cramer's rule to our spring mass systems. So the one that we are considering is a coupled spring mass system. What that means is we have a rigid base here, and we're going to attach a spring number 1 to mass number 1, and we'll assume that that first spring has spring constant K sub 1. Then X of t is going to model the position of mass 1 above or below its equilibrium, and its equilibrium position we'll call X naught. Then we're going to couple that with another spring and another mass. That second mass is called M sub 2, and we're looking at K sub 2 for the spring constant there. We'll assume that the equilibrium position for mass 2 is Y naught. So again, X of t is the position of mass M1, and Y of t is the position of mass 2. Don't forget that motion above equilibrium position indicates a negative value for X. Below, where the spring is elongated, is a positive X, and the same thing for Y. If Y moves above its equilibrium position, that compresses the spring. Y is less than 0, and below, Y is greater than 0. So looking at the system that models this entire spring mass coupled system, we could say Newton's second law, mass times acceleration. So mass 1 times the acceleration x double prime is equal to the opposite direction for Hooke's law, negative k1x. Okay, but mass 1 is not only affected by spring 1, it's also affected by spring 2. Remembering that x is the elongation of spring 1 and y is the elongation of spring 2, we need the net elongation or the net change in the position of the mass when both of those springs are stretched. This is going to look like k sub 2 times y minus x. So this is the net elongation of both of those springs. Applying Newton's second law to the second mass, we have mass times acceleration, or m sub 2, y double prime. The only spring affecting mass 2 is k2, but it is affected by k1. So in this case, we're going to have negative k2 times y minus x. Again, y minus x is the net elongation there, and this part is Hooke's law only. So that is how we're going to set up the system when we have a coupled spring mass system. So let's apply this to our last example for this section, example 5. Consider a coupled spring mass system with mass 1 equals 2, m2 equals 1, k1 100, and k2 50. Assume the motion is free and undamped. Free motion means I'm not going to interfere with the base. It is rigid and fixed, which means we're going to be dealing with a homogeneous system. Free motion indicates that there's no damping, there's no resistance to the velocity of those masses, and these two equations will model our system. So plugging in our specific constants, no units are given here, To keep it very simple, plugging in our constants, we can set up our system as follows. We have mx double prime, so 2x double prime equals, now we have negative k1 times x, so we have negative 100 times x plus k2 50 times y minus x. So again, using this model, just plugging in our parameters. Next, we have m sub 2 y double prime. M sub 2 is 1 equals negative k2 times y minus x. So that models our coupled spring mass system. Now, let's rewrite this using operational determinants. It's convenient to write these in standard form, so let's rearrange this a little bit. I'm going to do some quick algebra right here. That's 50y minus 50x, so that I can combine like terms. We have 2x double prime. On the right side, notice we have a net of negative 150x. I'm bringing that over here to the left. And we're subtracting 50y, leaving 0 behind. I'm going to do a little bit of quick algebra here as well. Just writing it down so I don't mess it up. And moving everything to the left side, starting with our x. So we have negative 50x plus y double prime plus 50y equals 0. How's that look? I hope that it's correct. We don't want to mess up this early in the system, right? Okay. Next, let's rewrite this system using operational determinants. So the first equation can be written 2d squared, that's a second derivative, plus 150 times x minus 50 times y equals 0. Second equation, negative 50y plus d squared, that's a second derivative, plus 50 times y equals 0. Notice that this system is homogeneous. That makes this particular method a lot easier. Let me backtrack up here for just a second. If the system is homogeneous, then both of these functions are going to be 0, and the determinant on the right side is going to be 0. That's going to be true for this as well. This entire determinant is going to be equal to 0. So the operational determinant applied to x and the operational determinant applied to y is going to yield the same characteristic equation in either case. Since we're dealing with a homogeneous system, that means we can apply a shortcut here. That's good news because these are pretty long problems. Let's go ahead and just calculate our operational determinant. That is the determinant 2d squared plus 150, negative 50 over here, negative 50 here, and d squared plus 50. Our forward diagonal product looks like 2d squared plus 150 times d squared plus 50. And we're going to subtract our reverse diagonal product. That's negative 50 times negative 50. This gives us 2d squared plus 150 times, let's go ahead and FOIL here. How about 2d to the fourth plus, let's see, outside terms we have 100d squared, inside 150, that gives me 250d squared. 150 times 50, I'm going to grab my calculator here. 150 times 50, my brain's kind of tired. And we're going to go ahead and subtract here 50 times 50. And our net result is plus 5,000. Okay, that is our operational determinant, and this will be applied to both x and y. So we have 2d to the fourth plus 250d squared plus 5,000 times x equals, remember, the determinant on the right, because it's homogeneous, will be 0. Let's go ahead and reduce this a little bit and divide everything through by 2. We get d to the fourth plus 125d squared plus 2500 x equals 0. And keep in mind, it's going to look exactly the same if we have a y right here. Also, the characteristic equation is going to look just like our operational determinant. So what I'm going to do is actually use the operational determinant as the characteristic equation. The only difference is this one has a d, the other one would have an r. Okay, can we factor this? Let's give it a try. Oh, it's not so bad. How about 125? Okay, so it looks like we're going to end up with complex solutions. D squared would give us negative 25 or plus or minus 5i here, and plus or minus 10i here. Okay, so translating that into a solution, and remember you can do this in any order. We're going to call this C sub 1 cosine 5t plus C sub 2 sine of 5t plus C sub 3 cosine of 10t plus C sub 4 sine of 10t. Okay, now here's the shortcut part. Since we're dealing with a homogeneous system, if I were to repeat this for y, I would get exactly the same roots and I would get exactly the same expression here, except I would have 4 more constants. And then I would have to do the necessary work to reduce the number of constants like we did up here on example 4. So we're going to use a combination of the operational determinant method and the substitution method we learned at the beginning of the section. So instead of using the operational determinant to find y, I'm going to go back to the original system and simply find y by substitution. That way I won't have to work so hard to reduce the number of constants. So I need to find a convenient equation where we can express y in terms of x. So if I'm looking at, this one looks pretty convenient, I will be able to isolate y and express y completely in terms of x. So I'm going to do that here kind of as side work. I'm going to rewrite the equation that I've chosen to use. And I'm going to solve for y. Let's divide through by negative 50. So y is going to be 1/25 x double prime plus 3x. Looks like we're going to need to find a couple of derivatives of x. So first derivative is negative 5c1 sine of 5t plus 5c sub 2 cosine of 5t minus 10 c sub 3 cosine of 10t plus 10 c sub 4, oops, that should have been a sine, and this one will be a cosine. Okay, we need a second derivative. We have negative...
I can learn to understand.
Negative 25 c sub 1 cosine of 5t minus 25 c sub 2 sine of 5t minus 100 c sub 3 cosine of 10t minus 100 c sub 4 sine of 10t. Now that we have the second derivative, we can go back to this guide and determine our solution for y. Y of t equals 1/25 x double prime So I'm going to take 1/25 of this term plus 3 times this term. So that's going to give me negative C1 plus 3C1, or 2C1 cosine of 5t. Doing that same thing for the second term, looks like we're going to get another 2C sub 2 sine of 5t. 1/25 times this constant plus 3 times this constant, that's going to give me negative 4 plus 3C3, or minus C sub 3 cosine of 10t, and minus C sub 4 sine of 10t. So I hope you understand that we are doing a combination of methods on this last one. We started out with operational determinants, but we are taking advantage because it is a homogeneous system. We're finding the second half by substitution. Okay, so compare it to what we did up here. We found x using operational determinants, and then we found y using operational determinants, but we had to do some work to reduce the number of constants in the system. Down here, we didn't do that second round of the operational determinant because we have a homogeneous system. If we have a homogeneous system, then y is going to look like this, but it's going to have constants C5, 6, 7, and 8. So we sort of took a left turn away from the operational determinant method here and went back to substitution. I went back to the original system. I found the relationship between x and y, and therefore I was able to find y of t by back substitution. Now that we have the solution, let's analyze the motion of these two masses. Comparing our two functions, x of t and y of t, we've got some similar terms. Notice in x of t, we've got two trig functions, a sine and a cosine, with the same argument, and a sine and a cosine with the same argument here. Okay, what that means is that these two are related, and these two are related. If we wanted to use our trig identities, we could condense both of those into a single cosine wave. If we did, we would find out that these two form a cosine wave with a period of 2 pi over 5. So in this case, the two masses are going to be oscillating in the same direction, but the second mass has amplitude twice as tall as the first mass. Okay? Mass sub 2, let me say it this way. Masses oscillate in the same direction. And I can tell that because the coefficients all have the same sign. Okay? However, the coefficients of sine and cosine in the function x are not as big as the amplitudes here. So the amplitude of mass 2 is twice the amplitude of mass 1. Okay, so again, we could condense those into a single cosine wave, and what we would see is at some point in their oscillation, with a period of 2 pi over 5, we end up with something like this. So mass 1 following a cosine wave would have amplitude half that of mass 2. But notice they would pass through their equilibrium at the same time. And again, the period here is 2 pi over 5. Looking at this second pair, again, we could condense those into a single cosine wave, but it's not necessary. We can make our observation here. The period of oscillation is a little different. So they get out of sync and then they fall back into sync here. The period would be 2 pi over 10 or pi over 5. Notice how the coefficients have opposite signs. Whoops. So the masses oscillate in opposite directions, but they have the same amplitude. So if we make a a quick visual of what's going on here. The masses are oscillating with, again, the same amplitude. There we go. But in opposite directions. Okay? So my computer screen is really warm, and sometimes it makes it hard to write and it doesn't pick it up as well. So I think that is enough for one section. That was a lot of details, a lot of things to pick up on, but you have enough information to go get started on your homework. Hope y'all have a great day.